This is the third of 4 videos on thermochemistry, and I just wanted to make a very important, point here at this transition. We're going to leave kind of the heat idea, where we had kind of at the very beginning this basic idea that if we have conservation of energy, and we do, that heat into, we had put an example of water, heat into the water from a hot block was going to be equal to the heat out of the hot block. And we set up the equations for that, the mass times the heat capacity times the change in temperature for both those sides. And we could do some great things with this equation because it's, again, a zero-sum game. You never lose energy. So we can set the energy of the system to a surrounding. And we just picked one here. We didn't pick necessarily, wasn't very important who was the system and who was the surrounding. But in the second video, we started to move away from just arbitrarily picking system and surrounding. We started talking about change in energy. If it was at constant volume, some system, some reaction, then we could say Q was equal to that. But then we made a very important transition. We said that we can have a change in enthalpy, which looked at just remembering that there's going to be some amount of heat that's kind of sometimes lost to this reaction. Now we're going to be talking about chemicals producing a gas, and the gas being pushing away the atmosphere, or the reaction is making more gas molecules than it initially had, so it tends to push back the atmosphere as it expands into the product state, because the more products have more gas. So that'd be a work. And so we just kind of said there's going to be some amount of energy that goes into work, and we're not going to worry about it. We're going to still consider this as heat, just heat at constant pressure. So we can say maybe Q at constant pressure, pressure constant, because that's the only other way the energy can be changed is heat and work. So we can say this enthalpy term was important. Now in the third video, I just want to make sure that you understand when we start talking about change in enthalpy, we are always talking about the physical state or chemical state of, chemicals. So we're talking about, solid to liquid. We're talking about reagent A to product B. So we're talking about A as a solid going to A as a liquid. We're always talking about compounds. So I just wanted to make that important sort of statement that as we go into this third video looking at enthalpy, when you hear enthalpy, you think, oh, I must be talking about a chemical. And here's a perfect example. On the last slide of the last video, we looked at the amount of heat that was absorbed by the water, was just a surrounding, from this reaction. This is a chemical change. But we said we can kind of separate the chemical change from the amount of heat that went into the water, the surrounding. So we did the surrounding first, and that's always easiest. So we got the amount of heat exactly that the water absorbed from this reaction. Now we'll look at the reaction. And again, we're remembering that enthalpy is now our term because we're looking at Q at constant pressure. That's what enthalpy is. Now we'll get into more of enthalpy and state functions in Gen Chem 2, and more. We're going to look more at this equation. But for now, let's just keep a hold of when we're talking enthalpy, we're talking about reagents or some chemical, and we're talking about them changing the heat in and out at constant pressure. So in the reaction, we had H plus reacting with OH minus, and so much of these two. Well, how much? 0.1 moles and 0.1 moles. So this is the balanced reaction that we're finding the enthalpy for. Now, we're just going to come up in class that we don't look necessarily at 1 mole to 1 mole to 1 mole. We balance the equation, we get it to the lowest coefficients, and we say we have an enthalpy of reaction for that reaction. We talk about it in kilojoules, and now we leave it at that. Kilojoules per 1 mole of water, if you want to say that. But we could also talk about it when it's in 2 moles plus 2 moles makes 1 mole. We'll see that more as we apply this term, enthalpy of reaction. It's for the whole reaction, whatever the coefficients are at. So what we can do is we could take and divide that 500 and 51 kilojoules, because we know that's the exact amount of heat that the reaction lost, and so we're going to say minus 551.76 joules, because that's what this gave up as heat at constant pressure. And we divide that by our 0.1 moles of, and we'll just say for this case, water. It doesn't matter because these are at 0.1, but we have to get them to 1, because 1 to 1 makes 1. To get the enthalpy of reaction to match up with this equation, we can't leave it at 0.1 molar, because these are all at 1, 1, 1. So we have to divide it, and we will have joules per 1 mole of H plus, or for 1 mole of water, we'll say. So when we do that, of course, you just move the decimal point. It's going to be 5,517.6 joules per mole of water. If you want to say that, that's fine, but it's, again, always this amount for that whole reaction. We could change it to kilojoules and say 5.5176 kilojoules. Would also be acceptable. All right, now let's keep going with enthalpy, because we're going to use that term a lot in these last 2 videos. So what we can do also is, because people have done calorimetry at constant pressure for a lot of different reactions, so we can look up in tables what they've found for the enthalpy change at standard conditions for a reaction. So standard conditions are always going to be 1 atmosphere. When you see this little superscript circle, that's 25 degrees in 1 atmosphere. They've kept the gas reagents and products close to that temperature and that pressure. And it's for that reaction. So we can say for this reaction between ethanol, oxidizing or being combusted with oxygen to form CO2 and water, they found that the enthalpy, and this should be enthalpy for reaction, for this is minus 1235.7 kilojoules per mole. Now notice it's a negative here because this is giving off energy. This is the system, so to speak, again. It's giving off that much heat at constant pressure. And notice that we're saying, it says per mole here, but I really want you to realize this is kind of a weird term they put in here, because it's this energy per 3 moles of water. It's this energy per 2 moles of CO2. It's this energy per 3 moles of oxygen. So I often tell students just to kind of maybe say is, kind of make it make sense by saying this is the amount of heat per reaction, reaction. So it's kind of more vague now, and you can divide it by these numbers later if you need to, but this is the amount of energy for this reaction. 1 mole plus 3 moles, making 2 moles plus 3 moles, gives you this much heat kicked off. So that's standard energy of reaction, standard enthalpy, of reaction. The standard enthalpy change of formation is different. Now here we had 1 plus 3 moles, but for this it's always going to be, we take the elements in their standard form and just 1 mole of each, the amount that it takes to make 1 mole of our product. The standard enthalpy formation of a compound, 1 mole of it, is the enthalpy change which occurs when 1 mole of the compound is formed. So we can't have 2s and 3s. You have to have, when you're talking about standard enthalpy of formation, you're typically talking about 1 compound and you're talking about 1 mole of it. So it's formed from its elements at standard states. Not any way to get to this, but it's from the elements that you form this 1 compound and 1 mole of it. So the standard enthalpy of formation for iron oxide is minus 824 kilojoules. Now you can say per mole of iron oxide. Now this one's more specific. Per mole of iron oxide. This is how much heat you get for 1 mole of this formed. Alright, I'm going to do one last thing with all these standard enthalpy of reactions and standard enthalpy of formations. We're going to use what's called Hess's law. Hess's law is just a law that's describing an indirect way to find any heat of reaction. So the energy change in the overall chemical reaction is equal to the sum of energy changes in the individual reactions comprising it. And it's kind of that mountain idea again, where I can have point A, B, and C. And according to thermodynamics, it doesn't matter if I go A to B and then B to C, that still would give me, in the end, A to C. So Hess's law typically looks at the indirect way to get to some particular some particular product. And Hess's law looks at the indirect way instead of looking at the direct way, because maybe there's not some data on that, or it's just harder to find that data. We can say, well, if I can go from A to B and have the enthalpy for that change, and then have the enthalpy for B to C, then I can sum those together. So that's kind of the idea behind Hess's law. All right. So the way we can look at it then is we're trying to find the enthalpy of reaction for this reaction shown down here. This is not a standard enthalpy of formation, because we're not looking at just one compound formed from elements. This is not an element. But we can use some standard heats of formation here to come up to this. So here's what we can do. We can say, oh, I see CO2 is on the product side, so I'll use this one as is. We'll keep it kind of in this form. Over here I have water, and this one has water being formed, so I'll use this one as is. But this one, I noticed the methane is formed as product here, but it's the reagent in this reaction we're looking for the energy or enthalpy of reaction 4, so I'll sort of flip this one. You get to flip it. So on the next slide, we're going to take this one and we're going to have to flip it, because we're not making methane, we're making, I guess, our CO2 and water from methane. So let's do that. So we're going to take these energies. Oh, I forgot. This one, we notice that there's 2 moles of water. So I'll just times it by 2 as it is. Times it by 2. So we're going to take this and multiply it by 2. So I have the next slide where we do all that, I guess, work. We've flipped, I guess, the value. This here, we needed to make a reagent, so we did that. It's now a reagent. It matches up with this. And we had to then flip. If we're flipping the reaction, we have to flip the value for enthalpy, because you're going backwards. So it's now plus. We kept the other ones as is, but we multiplied this one by 2, so it's minus 571 instead of just minus 285. And we now add all that up. I want to say something before you add everything up. Just make sure that it all comes to, as you sum up these 3 different reactions, it better come up to this. So let's check that first. So CH4, yes, I have one, and I don't have anything else down here that's CH4, so I'll bring it on down to the summation. Yes, we have that. 2 oxygens. Well, if I take and multiply this by 2, that gives me 1 oxygen here and 1 oxygen here. So yes, we do actually have, when you sum up the 2 oxygens, you get 2 down here. This was a 1/2 times 2. So I gave this a value of 1. 1 plus 1 is 2. The CO2, we see that over here. So we'll check on these. And then the water, we multiplied it by 2. So yes, we do have 2 water molecules. Now there is something interesting. These go away. The carbons here cancel out. One's on the product side, one's on the reagent side. They cancel. They don't make it into the bottom summation equation. So just like we brought everything down here to sum it up, we do the same thing here. So I'm going to take my handy dandy calculator. And so we made sure, that was step 3, we made sure that we netted the right equation. So I'm going to take the 74.8 minus the 393.5 equals, and I'm going to say minus 571, because we had taken and doubled. So we get minus 890.36, and that's going to be in terms of kilojoules. So this is the enthalpy for that reaction. I'm just going to leave it at that instead of saying per mole, because it's for the whole thing. We are done. That's hard work. That's called using Hess's law, where it's an indirect way to get to this enthalpy of reaction. Thanks. Bye-bye.